Thank you. Okay. Same ground rules as yesterday. Something you don't understand, raise your hand, bother me, jump up and down. We'll figure it out. Okay, today I'm going to, this is actually one of my favorite books. I couldn't resist. Yertle the Turtle, King of the Pond. And we're going to use some of the things that we built up yesterday to get higher and higher till eventually we're going to fall. So each person falls at his own pace. But I'll try to use some of the concepts that we learned about simple fracture in order to explain things that are a bit more complicated. And more or less towards the end, I'll bring you up to speed on things that are more or less at the front of the field now. So not everything, but just to give you a taste of what people are working on and what we don't know actually. But okay, we'll take it one step at a time, or one turtle at a time. Okay. So let's quickly summarize what we talked about the last time, just for fun. Okay, so we looked at simple cracks. And what are simple cracks? Cracks that don't have any instabilities. They just very boring cracks. They move, they accelerate, but they don't change their shape. They don't bifurcate. They don't do anything special. And we understood, the first thing we did was we looked at the equation of motion. And this will be appearing here and there because we'll need to refer to it at times. Just to remind you, this is the instantaneous velocity of the crack. This gamma is the energy dissipation, the energy that the crack needs to dissipate, the energy to create a new unit area of broken bonds or whatever. That's gamma. A big G is just the energy flow into the tip of the crack. Remember the, should have brought a piece of paper here. Can I borrow a piece of paper? Anything, yeah. We're going to repeat this momentous experiment that we just looked at, we did yesterday. Thank you very much. Okay, this experiment actually doesn't work with toilet paper, but any other paper it does. So things are very, very tough. When we make even a small crack, the singularity at the tip of the crack weakens the material and then breaks bond by bond in front of it. So we have a stress singularity at the tip of the crack. Now, we took energy and we inserted it into the entire sample. And that's what G, but it all flows into the tip of this, into the tip of the crack, into the singularity. And this G is just the energy flux into the tip of the crack. So this is telling us that the instantaneous velocity is dependent on, it has an asymptotic velocity, the Rayleigh wave speed. Remember, that's this, the speed at which a disturbance moves along a free surface. And it accelerates as G progresses. So gamma is a material constant or material function. And the longer the crack gets, in general, the larger G is, this thing gets smaller, so then V will accelerate with the instantaneous length of the crack until it reaches this asymptotic velocity. One funny part about this equation of motion, which is very strange for physicists or for anybody actually, is that V instantaneously depends on all of these things. There's no V dot There's no time derivative of V here, so there's no acceleration dependence. If gamma will change like a step function, according to this, V will jump immediately as well. We'll see that actually happens. For large systems, V has no inertia. It behaves like a massless entity, or the crack behaves like a massless entity. Okay. Then we looked very more closely at the structure of the singular fields at the tip of a crack. And we found that if we look back, we saw that the assumptions that lead to fracture mechanics, there was a contradiction because fracture mechanics assumed that all of the deformations are small, so linear elasticity is valid. But as you get near a stress or a strain singularity, obviously this fails. We took this into account by deriving a weakly nonlinear theory, taking nonlinearities of the stress-strain relation into account. And when we took just the quadratic nonlinearities, we found that the singular fields actually got more singular. So we had the singularity became, instead of 1 over the square root of r, where r is the distance from the crack tip, it became 1 over r, which is worse as r gets closer and closer to the tip. We also saw that a new intrinsic length scale emerged, which we called the L nonlinear just for fun. And this came as directly as a result of the effect of the nonlinearity at the crack tip. And this will be the star of our show today. So remember that there's this extra length scale that comes into play. Now, if we just took the predictions of linear elastic fracture mechanics, all of the, as one approaches the crack tip, all of the relevant fields scale as 1 over the square root of r. Okay, it's a power law, so there's no scale, there's no intrinsic scale there. Once we have a different power that's coming in, then the meeting of these two power laws, where they match, defines a scale. And that's what this extra scale is. And this will play a large role. This is a microscopic scale. It will play a significant role in dictating or governing the macroscopic dynamics of cracks as they break material. Okay, so what we're going to be doing today is understanding, to a point at least, crack instabilities using this new scale that we found. Okay, so we're going to see again how microscopic structure affects the macroscopic behavior in the sample. Does anybody have any questions or something before we start? Okay, good. Thanks. Yeah. You're right. Okay, it's a first step. In other words, what we're doing is expanding the constitutive relation. So this won't be enough as we get closer and closer to the crack tip, and it's not relevant too close. In fact, one has to do more. I hinted at what one has to do, but I didn't show it at the end. So it's only relevant as long as this expansion is relevant. So you're absolutely right. It does extend linear elastic fracture mechanics, and it extends it enough in order to define the scale. Now, the difference between where this breaks down and the tip of the crack is actually only a few microns. It's not a huge, because everything is becoming more and more singular. So the distances are not great, but the effects, if one takes larger, one can do an asymptotic calculation where one assumes that the strains are very large. And then you can do a different calculation for the strains just at the tip. But when you put them together, you get this nice picture of a simple crack. But you're right. But at any rate, we'll be using this guy to try to understand what the crack is doing. Yeah, so there's a region, okay. Okay, this is our crack tip. It's parabolic. Okay, this is where linear elastic fracture mechanics is relevant. That's this dashed line here. The relevance of this weakly nonlinear approach will take us here. Okay, so that's closer to the crack tip. Over here someplace, use a different color. Okay, that's the region where gamma lives. That's where dissipation takes place. Because at the tip of the crack is where you're actually breaking bonds. And we won't even touch on the structure of that today, but that's a very good question that's people are starting to look at now to try to uncover the structure of this, of the dissipative region. So we're assuming that everything is elastic up until this area. It can be linear elastic, it can be nonlinear elastic. Okay, so this is our nonlinear scale here. Okay, but things are still elastic here and actually even elastic until there. What do I mean by elastic? It's related to, this is a potential as a function of the distance between two neighbors or something. I'm drawing something like Leonard Jones. Linear elasticity lives here. We're breaking things. Okay, so we're over here already. And what we've done is take into account the nonlinear contributions. So that was basically the sketch of what we did yesterday. And this is what you all learned and know and love from kindergarten or not. This is Hooke's law, stresses and strain are proportional. Here, just the first correction that they're not. And in the case of the brittle gels that we're looking at, we know precisely what the constitutive relation is. So we don't have to guess what this nonlinear contribution is. We know we can measure it. Okay, good question. Any other questions, comments? Okay.
Sorry, Professor Fineberg. So before it starts, so I would like to announce that there is a mic on every table. So whoever wants to ask any question, please use the mic and ask. Okay.
Okay, I guess that's for the people at home or something. Okay, anyway, this is what we'll be doing. So we're going to look at the origin of dynamic path instabilities, either spontaneous oscillations of the crack as it gets faster and as it gets at very high velocities, or spontaneous bifurcations, which we called microbranching. So we're actually going to show that these two instabilities are related to one another. And they're related through this mysterious new length scale. Then, okay, our experiments assume the 2D world. But at the end, we're going to look at what happens when the crack, now it's not, if one assumes that this has a width to it now, it's not a singular point, it's a singular front that's moving through the material. And we're going to be looking at the dynamics of this front, a little bit of the dynamics of this front. And that's going to help us understand why these microscopic branches die. So we're going to be, now this talk will be a bit more complex than the last talk. So hold on to your seats, because we'll be using stuff that we've developed last time, and I'm sure it's not sitting perfectly over here with everyone. So again, if something isn't clear, let me know. We don't have to get to the end of the talk. We just have to get to lunch or the coffee break. So it's more important to me that you understand whatever you understand than to finish all the material. I'm fine with the material. I know it. You can ask me questions or something, but okay, so we'll take it slowly because once again, we're building one thing on another. And at least for me, when the tower of turtles gets too high, it often tumbles and then you get a total reset. So I don't want that to happen. So we'll take it as slow. Stop me if there's something that you don't understand. Okay. Now, yesterday, we talked about mode 1 or pure tension. And today, we're going to bring into account small perturbations of shear of mode 2. And we'll see what that does, how that affects garden variety cracks. So our applied loading is totally tensile, that's mode 1. But just remember, mode 2 exists, and all of these fields are, as we get near the singularity, not too near, because this is still the linear elastic solution for cracks. There's some k divided by the square root of r, on some universal function or whatever. K1 relates to mode 1, K2 relates to mode 2. Okay, so whenever you see a K2, it means that there's a shear component. Okay, this will be an experimental talk, so just briefly we'll mention what we're looking at. So again, we have a thin sheet of scientific jello, polyacrylamide for the experts, visualizing it from above while illuminating from the bottom. Now, one thing that we'll be using here is that one surface of this gel, we've inscribed a very dense grid. In fact, you can see a picture of a crack moving through this grid. In a minute, I'll zoom in and you'll see the grid itself. In fact, here it is. Okay, so this is a 50 by 50 micron grid that we've imprinted on the surface, on one of the surfaces of the sample. And this allows us to, by looking at the distortions of each one of these squares, we can actually measure in situ the strains, the deformations as a function of wherever we want to see. So this is not trivial to do. But once we have it, it's a great tool because one snapshot gives us the entire strain field. And this also carries with it the reference frame, because each one of these guys initially was perfectly square. And we know that. And we also can label these guys. So this is number 1, 2, 3, and so on. So it makes life, it's a nice technique which makes life much easier for us. There are similar techniques around where people look at scratches and look at deformations by looking at correlations of scratches. This I like better because it just carries with it the reference state being what the material looks like when it's totally relaxed. Okay, so we'll be using this in a second. Now, in the last talk, we saw that we understood simple cracks that don't become unstable pretty well. So we're going to look at what happens when cracks stop being simple. And the instabilities that I'll be talking about are, this is a cartoon version, of course, the microbranching instabilities, where you can see that a crack, the main crack runs along and it develops these microscopic side branches that propagate, but they die. So they're all very limited, few hundred microns at most in length. And we also saw that if we can suppress this instability, then the crack gets to high velocities and then spontaneously undergoes oscillations. So we're going to try to understand both of these in terms of this nonlinear lane scale. Okay, let me just show you some movies, just to remind you. So this is a movie of a crack that undergoes microbranching. So it's moving faster than this critical velocity for microbranching. And you can kind of see these little things, and those are microbranches. So we have the main crack here, it's wiggling and such, but in this experiment, but these are the things that we want to understand. And when a crack undergoes a bifurcation from a straight crack to microbranches, then its velocity, its instantaneous velocity oscillates all over the place, it fluctuates. This is in these brittle gels that we'll be talking about, and the same thing happens in glass. This I showed you last time. And the form of each one of these microscopic branches is identical for many materials, for all brittle materials that we've measured. They also have a three-dimensional behavior. So this is our two-dimensional sheet, and this is the third dimension that's hidden. So this is the thickness of our sheet. And these are photographs of the fracture surface after the fracture passed. And each one of these things is a microbranch. So each one of these microbranches bifurcated, died, the crack ran forward, then we get another microbranch and so on and so forth. This is the surface, and they propagate along kind of directed lines. So you have regions of the fracture surface where the surface is very smooth, featureless, and these regions where the microbranches take place, and they're localized along the width of the sample. And the same thing happens in glass. Okay. Now, this already hints to the fact that microbranches are hysteretic, they're bistable. Locally, a crack can be either in a smooth state or in a microbranching state. And in this case, you see that they're happening at the same time. We'll get back to that in a few minutes. Okay, now if we suppress the microbranches by making the materials thinner and thinner and thinner, then we get to the oscillatory instability, which I'll show you now. So here's a crack that's just kind of barreling along, getting faster and faster. Once it reaches about 9/10 of the shear wave speed, it starts to spontaneously wiggle. So we want to understand, and the first thing that we'll try to do is understand these wiggly cracks, the oscillatory instability. The thickness of the system here is about 200 microns. So these are pretty thin. Yeah. It's expected, well, okay, the fact that the material runs towards it, the free surface. Yeah, because the stresses are very large. And so basically what you're seeing is, I'm not sure how much, I assume that everyone knows linear elasticity, but I might not, it might be right, might be wrong, but there are two coefficients that dictate linear elastic material. One is the Young's modulus, or the spring constant, and the other is the Poisson ratio. Okay, the Poisson ratio means that if I pull this way, the system contracts that way. Okay, so what you're seeing is this stress singularity, as it reaches the free surface, is pulling the free surface towards it because of this Poisson contraction.
So, so one thing I'm wondering is that when the stress applied is constant throughout, why the velocity of the crack keeps on increasing?
Good question. This goes back to the scaling analysis that I used to derive the equation of motion. And if we're in an infinite system, the only scale is the scale of the crack. And then one can ask, okay, how much what's the size of the region that's effectively being influenced by the size of the crack? Where is the potential energy being most released? Well, the only scale in the problem is the length of the crack L. So this region has to go like L squared. What does that mean? As the crack gets larger and larger, this ball of potential energy that's being released and driving the crack is getting larger and larger. So for these boundary conditions, for a large system with constant stress at infinity, it just more and more energy is flowing into the crack tip. And you're seeing the result of that.
So for the infinite sheet, we'll have the self-similar structure of the crack.
Yeah.
In the sense, because we don't have any length scale.
Right. So what
And-
you see is a parabolic for the linear elastic framework. What you see is a parabolic structure that goes all the way to infinity, actually, and that goes like So that's a self-similar structure. That's the reflection of the 1 over the square root singularity of the strains. Why? Because integrate 1 over the square root of r to get displacements, and you get the square root of r. That's what you're seeing.
And we see some oscillations in this case. So do we see the similar oscillations in the case when we have infinite sheet, or it's just remains self-similar for all along in the sense?
Well, what we've seen is these oscillations have no connection to the boundaries. These are oscillations that create some scale, a wavelength. And that's a good question. Where is the scale coming from? And what I'll try to show you, it comes from this nonlinear length scale. So we formed a length scale because linear elasticity breaks down near the crack tip. And the crossover scale is this length scale. And this length scale will basically explain the wavelength of the oscillations as well as the oscillations themselves.
Thank you, sir.
Okay, yeah. No, in fact, I'll show you that it's how it scales. Okay, I'll change the material properties of the gels because that's what I can do and still see something, but I can change them dramatically by playing with the chemical composition. And you'll see that each one defines a nonlinear length scale, but everything scales with that. But I'm already giving my entire talk or something and answering the questions, which is good because you'll see it all this again. So any other questions? Yeah.
The fact that gels and glasses, you see similar types of those branchings, was that surprising, or like, did you expect that, or?
Well, the whole thing was kind of surprising. Did we expect it? In retrospect, we expected everything. At the time, it was this idea that brittle materials should break like brittle materials no matter how they are. And it sounds reasonable, but when you look at things that are 3 orders of magnitude softer, or 6 orders of magnitude softer, then you think, okay, maybe it breaks down. It started as a student project because I didn't really believe it too much. I didn't want to give it to anyone as a PhD and have them waste, 5 years of their lives looking at Jello, although it's happened since. But so I gave undergraduate student this as a project. And as it started to develop, we were more and more surprised. So yeah, this was usually nature tries to make life more difficult for us. Sometimes it helps us. And then it makes life more difficult for us. So, okay. Just to remind you about fracture mechanics. So we looked at this. We derived this nonlinear scale as the crossover scale between, this is the solution for linear elastic fracture mechanics, and the nonlinear term has a 1 over r singularity, and the crossover is this scale here. which will be the star of our show. Okay, we had seen these instabilities, we didn't really understand them. And remember my theoretical postdoc, Eran Buchbinder, where is he here? His name will show up soon. As a theorist, I really had nothing to do with him, so I told him to go away and find something to do. And after he came up with this nonlinear theory of fracture mechanics, I thought that enough was enough, but no, he was bored. So I told him, okay, see if you can figure out this. So he wrote a paper, and he showed, what he did was he related this wavelength, this is a spontaneous wavelength, to this nonlinear length scale. And what he did was this. He said, okay, far away from the crack tip, everything is linear, everybody's happy. We have the material organizes itself according to linear elasticity, because that's all it knows, that's all it needs. As we get closer to the crack tip, the material starts to be stretched and stretched and stretched, and it actually changes some of its characteristics. So in a sense, we can think of this as the head of the dog, and this is the tail of the dog. Okay, so the tail of the dog is feeding the head, but the head of the dog, well, we'll get to the fact that the tail is wagging the head, but okay. But this reacts according to the characteristics within this nonlinear zone, which is really, really stretched, okay? So energy is being fed, but there's a phase lag because it's a different material. So in a sense, there's some kind of material mismatch at the boundary. And so this material reacts to the energy flowing into it, but not instantaneously. Okay, so that's what this is saying. So the stress intensity factor, or the singularity at the tip itself, if it's a function of time, it reacts with this to the stress intensity derived or developed at large scales with the phase lag. And the phase lag goes like the time minus the size of this zone divided by the shear wave speed of the material. Okay, so then what Eran did was he said, okay, I'm trying to understand a wiggling crack. Okay, what can drive a crack? Let's talk about a straight crack. What can drive a straight crack off axis? So he said, okay, let's look at the stability to the imposition of a perturbation of shear. Because if I shear the crack tip, the crack is going to bend according to the shear that I apply. So this was the intuition. And the theory is kind of heavy, so I won't go into it. He really loves these intractable integrals. So people that love that can look at this paper. What he found, though, was that this delay time, well, okay. Okay, what he predicted was that the wavelength here has to scale with a nonlinear scale. In other words, that's again, this is a scale that developed in the system. This is the only intrinsic scale that we have. So this is not particularly surprising that this is the prediction, because it's the only thing that he could have predicted. But what he did was a bit better. So here are the predictions. So first of all, he predicted that at a critical velocity, this phase, the out of phase relation between the energy flowing into the crack tip and the response of the crack tip already feeds back and does create a linear instability of the crack tip, and there is a critical velocity. So the critical velocity they predicted was 0.8 of the shear wave speed. What we measured is actually 0.9. So he screwed up there, but okay, he's a theorist, what can you do? This is the, as a function of all of these different colors are different materials with different Young's elastic moduli, different fracture energies. Okay, so this is the experimental observation that this critical velocity is always around 0.9, no matter, this is a function of the Young's modulus of the material. And another experimental observation was that the wavelength of this oscillation, it's scaled with, this is the nonlinear, nonlinear length. So what we saw was that there is this scaling, linear scaling of the wavelength with this nonlinear scale. And here in the table are just the different colors are different. So the Young's modulus change, we managed to change it by a factor of 6 or so, the fracture energy by a factor of about 3. So it's the non-trivial changes in the material characteristics, but they all fit, they all fall in this line. Okay, so what, wait a minute. Sure.
Is it possible to predict how the amplitude of the oscillations grow with time?
This is one that we never did. We measured it, but it wasn't, the measurements were not, we couldn't get a function out of it. We got, there was a lot of scatter or something. So I guess the answer is it might be possible, but it hasn't been done yet. So, but right now, well, actually, I'll show you some numerics in a minute, which might be able to, which might do that, but I don't remember that they mentioned it in the paper. So anyway, so this is a prediction of the theory, this linear scaling with the nonlinear length. And this also scales with this, this extra piece here. We called this delta for lack of imagination, the distance between the virtual crack tip given by linear elastic fracture mechanics and the real crack tip. So all of these scales are basically, they come together. And basically, okay, so the theory worked very well. And then Iran was not satisfied, really. So it took him about 10 years. And he convinced a friend of his to look at these numerically using a phase field approach. Okay, what is a phase field approach? Out here, it's just finite element using linear elasticity. So we're calculating all the fields. And now as you approach the nonlinear region, the idea is to insert a scalar field that behaves the Landau equation, roughly, or Landau-Ginzburg equation. And that basically, the scalar field defines the dissipative scale, okay? So you have linear elasticity, and then you can also add nonlinear elasticity in this region, and psi here is the dissipative scale. So these are the simulations, and this approach enabled one to self-consistently calculate what the crack is doing. Why is it self-consistent? Because this model for dissipation is fed by the linear elastic fields around it. So it's not, we're not just sticking in what we want, but it's a function of the energy that's flowing into the crack tip and so on. I won't go into the details because we'll go well beyond lunch, which is not a good thing. Okay, so this has a single dimensionless parameter in this theory, which is the nonlinear scale relative to the dissipative scale. And this scale is like the fracture energy divided by the shear modulus or the Young's modulus. That's the scale of the nonlinear scale divided by this dissipative scale. Good. Okay, let's see what they found. First of all, they had nice movies. Wait a minute, I missed one. Okay, so this movie shows what happens if you take the nonlinear scale basically to zero. So you're looking at linear elasticity that couples directly to dissipation. And what you'll see is a very boring movie, but I had to show it just to show that they actually saw boring cracks as well. And what you'll see is just a boring crack running across the, so same simulation, the velocities are already beyond the threshold for that we saw these self-oscillations, and nothing really happens. Okay, now this is what happens when the nonlinear scale is finite. So one finds very nice colored pictures of wiggly cracks, which is almost what we saw in the experiment. The only difference is the experiment was in black and white. We didn't make nice color pictures. But to summarize what we found, it's basically this. So we have the theory and the experiment, and they look qualitatively the same. And then quantitatively, okay, they see the same delta, or the distance from the crack tip. These are some of the experiments that we had for a given material that were not, they're not scaled in any way, or they're scaled by the dissipation size. And these are the simulations, so they agree very well. Now, it's funny because they could take nonlinearities that were softening or nonlinearities that were stiffening. So that means the effective Young's modulus, effective stiffness of the material increases or decreases with stress, because they can play those games on a computer. And it didn't matter. The only thing that mattered in these simulations was the fact that there was a nonlinear scale in the system. So you have either softening or hardening, but you still get the oscillations for the same reasons. Okay, so what we've shown is that, just to summarize this piece, that theoretically, we applied an infinitesimal shear perturbation to the crack, and we found that it became unstable at a critical velocity, which is relatively close to the one measured experimentally. And that both theory and the simulation showed that the wavelength scaled with the nonlinear scale. Now we're going to switch gears and look at our friend, the microbranching instability. Yeah.
Can you go back to a couple of slides?
To where?
Where you were showing the crack videos.
But
Back to that.
minute.
Yeah, so I can see initially the crack opening is increasing, but as you go back in time, you see the crack openings are now becoming smaller and smaller. What is the reason for that?
Ah, good. That's the same reason that the crack is accelerating and accelerating. Remember, as the crack gets larger, the energy flux scales with the size of the crack, or the length of the crack. Now, the curvature, or 1 over the curvature, actually scales also with K, with this stress intensity factor, which is a fancy word for the square root of the energy flux. So the higher the energy flux, the smaller the curvature of the crack tip. And so what you're seeing is that the crack gets, well, you don't see it very well here, but it starts more sharp and then gets more blunt as it's accelerating. So that's just a linear elasticity.
Of the crack. So if you look at the tail part, not the front, the tail part, there you see the opening has reduced a bit, the last.
Ah, okay. Good eyes. Okay, first of all, they're theorists. What do you want from them? Second of all, they're numericists. That's even worse. And they're limited by, so they did their simulations in a strip because they didn't have infinite computer time or something to do it. So what happens is, in fact, you see it. I could go back, but I don't remember where it is. When we looked at yesterday, the crack propagating in the strip. And when the waves come back from the boundaries, it tends to, this is the inertia that I was talking about. It tends to close the crack opening, crack tip opening. So initially, as the crack goes through the strip, it doesn't know about the boundaries, so it gets faster and faster. Once it gets to the strip, the waves start to come back from the vertical boundaries, and they tend to close makes it look like a tadpole. Okay. Okay, any other questions? Yeah. Very popular slide,
Yeah.
I see.
No, just
Okay.
just this slide.
Yeah.
The moment the oscillation starts, the tip of the crack, that forms some kind of asymmetric. If you look at the overall picture.
Right.
So ideally, once the asymmetric starts forming, then it should propagate in, it should create more asymmetric in the system. Then what makes it to drive into the, we are explaining in terms of non-linearity.
If it starts to go this way, why does it go back? Okay. My paternal grandfather once answered this question, when I asked him why, and he stroked his beard, and he looked at me with piercing eyes, and he said, "Why?" I said, "Yeah. Why is a crooked letter?" Keep that in mind. In other words, okay, in physics, the Y part, okay, I can tell you observations. One observation is theoretically that the instability that happens at the critical velocity is a Hopf bifurcation, which means it's an oscillatory bifurcation. Now, what are the mechanics of turning around and causing that? I don't really know. I'm guessing that it's something. No, I'm not even going to guess. I can tell you a lot of stories, but I have no idea, basically. Good question, but some things, well, okay, generally in physics, if one scratches any surface deep enough, you'll find another question. And this is where we stop scratching, at least for this problem. I'll think about it. If I can come up with a reasonable, intuitive answer, I'll let you know. Okay. So now that we perfectly understand the oscillatory instability, it's just being a perturbation or a response of a shear perturbation. Let's now look at the microbranching instability. Okay, and just to remind you, this is what the dynamics look like in gels and in glass. As the microbranch dies, or the microbranch is formed, the velocity goes down. Why does it go down? Because we're creating more surface. We need where the dissipation is larger. Because our dissipation is just the amount of surface that we're creating. The microbranch dies, all of a sudden we have a free crack who doesn't have all this baggage of extra surface, so it instantaneously jumps to where it should be if it was a single crack, a simple crack. But then it gets hit by the next one, and so on and so forth. So that's what we're seeing in the oscillations. Now, these are experiments in gels. The Rayleigh wave speed here is about 5 point something meters a second. So the critical velocity here is about 0.4 of the Rayleigh wave speed, and that's what we saw in glass or in brittle acrylics as well. So things start to go crazy at about 0.4 of the Rayleigh wave speed. In gels, though, we can do a little bit better because we can drive these things very hard. We can increase the amount of strain at the boundaries, and the gels will still hold together until we make a little cut and let the crack run. So we can drive it very hard. And what we found, first, we were very surprised that we can drive this critical velocity higher and higher as a function of the crack's acceleration. So we can make it accelerate more and more and push the onset higher and higher. And what we found was that the critical velocity was an approximate linear function of the acceleration. Now you might say, okay, there's a lot of scatter here. These are dirty experiments. I have no dirty experiments in my laboratory. Actually, there's no noise, or the noise in these experiments is the size of the dots. What this scatter is, and this is, it's telling us something about the physics of the problem. It's telling us that in order to transition to this microbranching state, a crack has to arrive, it has to be kicked by some localized perturbation, maybe a defect in the material or something like that. And the faster that it's, and there's a characteristic time, this is the delay time from the time that it reaches the lowest value of the critical velocity to wherever it actually goes critical, and it's a Poisson effect. So there's a time scale involved. This is the time that it takes for it to react when getting kicked by one of these defects or perturbations. Now, if it's accelerating very rapidly until you actually see the effect, is going to take, so the critical velocity that you'll see is going to be the acceleration times this time scale. And that's basically what we're seeing here. Okay, why am I showing you this? Because all of this is telling us, well, it's hinting, and I'll show you that this is a first order, the transition from a simple crack to microbranches is a first order phase, it behaves like a first order phase transition. In fact, the big test of a first order phase transition is in your microbranching state here, this is our critical velocity. If you're microbranching and you go below this and all of this shaded area, it's still microbranching, it's well below the critical velocity. So we see hysteresis in this transition. Okay. This is what this particular experiment looked like. So the line of branches at this point just went out of the off of the sample, and then it accelerated back to wherever it wanted to. Okay, remember this, but we'll forget about it for now. We'll come back to this in a second. Maybe. Okay. Wait a minute, I jumped too much ahead. Okay. For some reason, my computer. Okay. Okay, now our experiments, remember, we can measure the entire strain field around the crack tip instantaneously. So we can look at, for example, the component, the YY component, the stretching component, that's color-coded here, at a given instant in time. And so we looked at different, wait a second, I missed my big, wait a minute. I'm missing a slide here. I put in some corrections. No, okay, it's coming. Sorry about that. Computer got tired all of a sudden. Okay, So what do we see when we look at each one of these colors corresponds to one of these rings. So like the purple one is at the largest distance from the crack tip, and the green guy is at the closest distance to the crack tip. And what we see is this is each one of these is a function of the circumferential angle theta here, and you see bumps. You see basically symmetric behavior, which one would expect up and down of the system. Okay, the solution for mode 1 crack is symmetric around the axis of propagation. Good. Now you're saying, okay, yeah, I can see that. And there's a bit of noise there, but okay, more or less I can see that, you know, the thing on the left and the thing on the right are about the same. But then remember, my experiments have no noise. I have perfect students, perfect experiments, in some sense. If you look closely, you see that there's a little bit of asymmetry in the measurements. Tiny bit, but it's real. Now, it shouldn't be there because the solution for tensile cracks is, again, symmetric. Now, symmetry is a very strong thing in physics, so we should respect it. So this is telling us that, hope we get past this slide without, okay. So we can see this, we can measure this asymmetry. And we can see it getting higher and higher the closer we get to the crack tip. So here you can't see anything. Here you can't really see anything. Here it's a bit more, and as we get closer, it gets larger. So we're going to characterize this antisymmetric part, or this asymmetry, by just looking at the difference between this and this. So we're looking at the difference between the peak here and the peak here. We're going to try to characterize this asymmetry. And when we do that, we see that the asymmetry actually seems to look like it's becoming singular. And if we go and we fit it to a curve, what we find is that it goes like approximately like 1 over the square root of r. So this is behaving like a mode 2 component. Mode 2 components, remember mode 2 is under shear. It's exactly asymmetric, it's antisymmetric. So this is hinting at us that in addition to a pure tensile component, there's a little bit of a shear component there. And we can check that. Okay, so we see the 1 over the square root of r dependence that a shear component would, or singular shear component would suggest. And we also know from theory what the angular dependence is. So is this really, so this is at a given radius, this is the, this asymmetric part, this is the behavior of the asymmetric part of this signal with the angle. And we can compare it to the mode 2 prediction for the same value of this K2, this stress intensity factor for mode 2, with no free parameters, and it fits very well. So this is telling us that we really do have a singular shear component that somehow develops at the tip of this running crack. Okay, so I told my student at the time, Tommy Goldman, eureka, this was a eureka moment. So now we're going to be able to see, we now can understand microbranching. We should see some K2 component pop up immediately before the transition to microbranching, and we've solved the problem. Okay, good. So we did this analysis for a series. This is one an experiment where the velocity is increasing This is the point right before the bifurcation to microbranching. This is the point right after the bifurcation for microbranching. And this is our signal. And as you can guess, this was kind of a disappointment because there was nothing special here. We saw this oscillating K2 component for each one of these things, and nothing really special happened between this point and this point. We were not happy campers because it took her about 2 years to do these experiments. And this is like the final thing. And okay, okay. So out of pure desperation, we decided to like, okay, I don't know. Let's just take the value of K2 at the point right before the bifurcation and plot it as a function of the velocity at which microbranching took place. Because remember, we're getting a spread of velocities because of this acceleration effect. And when we do that, okay, these are the pictures of before and after or something. But when we do that, wow, okay, this noise actually became a function. So it's telling us that this is underneath this line. So this is the threshold for K2 that we measured when a crack bifurcated at 0.4 of the Rayleigh wave speed up to nearly 0.9 of the Rayleigh wave speed. And it's, this noise also all of a sudden became data. Not only that, what did we see? This noise, the amount of K2 that we need to trigger a microbranching bifurcation goes to 0 exactly where we see the onset of the oscillatory instability. Now remember, the oscillatory instability, the theory that was derived was, this is a perturbation, or this is a response to an infinitesimal K2 perturbation. Okay, so right over here, we need an infinitesimal perturbation to cause the crack to do something. Okay, in this case, to bifurcate to microbranches. And over here, all of these guys needs a finite perturbation to do it. And that's why, if you remember at the end of the last talk, I had the list of some of my friends, theorists, who have been trying desperately to look for instability of simple cracks, and they're all stable to infinitesimal perturbations of any kind or shape. But they didn't check whether they were stable to finite perturbations. We saw that the numerics saw a microbranching, but the theory couldn't find it. And why couldn't it find it? Because if we're looking over here for an instability and we're perturbing around there, we're not going to see it. It's stable. We need to give it a large kick to get to the second branch. And it's a hysteretic branch, so we need to whatever. Okay. So we find the systematic behavior. The higher the velocity, the smaller we need to go into this. And I'll call the microbranch a curved crack phase. Why will I call it a curved crack phase? Because I think it's a close cousin of the curved oscillatory instability. Why is it? Why did these disappear? We'll look at in a second. So again, the intercept of this line is exactly the critical velocity for the oscillatory instability. Okay, this picture basically, this picture basically supports this idea of bistability of a branch crack state and a simple crack. Have you guys learned about critical phenomena, phase diagrams and such? Okay, I see some nods, yes. You guys remember critical phenomena and phase diagram? I see some nods like this. Okay. a first order phase transition, for example, when you go from water to ice, it's not continuous, it jumps. And it has a large amount of hysteresis in general, or some finite amount. So if you're on like the water branch or something, and you go backwards very slowly so you can get to super cooled water at temperatures below the freezing, because you have bistability at that stage. You have two possible states the system could be in. The same here. Okay, we have a curved state or a branch state and a smooth state. They're both at the same velocity and they both can coexist. Now, when you have such a first order transition, so you need a finite kick to go from here to there. So this allows these things to coexist. So we also see that these have a strong spatial localization in Z, and we'll talk about that in a minute. And we can kind of wave our hands and explain all this as something called a transcritical bifurcation. So we have two branches. We have a straight branch, which can persist if not perturbed up till this point here, point 0.9 of the shear wave speed. And we have a curved branch that this is the hysteresis that we saw here. So we need a finite perturbation from here down to here in order to create this second branch. If we kick it as hard as we want here, it's stable to any size perturbation. Over here it goes, so once it's on this branch, it will stay there until it falls off at the end. Okay, that's what this phase diagram is telling us. And this is basically how we understand microbranches. Now, I have a few minutes and okay, time for questions, because I want this to sink in before I go to something entirely new but related. So, anyone have any questions, comments? Yeah.
While defining the noise, I think I have missed that part. How exactly you define in your system? How exactly you define your noise?
Good question. We have put in small beads into the system so we can perturb it, and then we can cause microbranching to happen. But these were spontaneous, which means probably that we have inhomogeneities in our gel that we can't even see by eye. But it's enough to, apparently enough to kick it.
So simply, if your system is not uniform or homogeneous, then we can say there is some amount of noise due to inhomogeneities. That might cause the branches of the thing.
Yeah. Now, where does the K2 come from, you might say? Because I showed you that there was this constant level, fluctuating but constant of K2. And that's probably due to, we take the plates and load them up into the apparatus. Maybe we twitched a little bit and did something like that. So there's a small amount of shear that's there, but we never noticed it. And that was actually going to dictate in retrospect where the microbranching took place. So it was sitting there, and then as the crack came faster and faster, it hit the critical, that level that was existent became the critical level, and then microbranching took place. So that's the picture that we have. Experiments aren't really perfect. There is some noise in the system. In retrospect, when we write the papers, we write it as if we put the noise in and we understood everything, but we never understand anything until we finish writing the paper in general. Other questions? Yeah. Okay. Remember, we had this little grid that we imprinted on the surface of the gel. So just by looking at how each little square deformed, we know what the strain is. Each deformation of the square gives us a deformation And we can then take derivatives and get the different strain components from that. So that's why it's a nice technique, because it's hard to implement, but it gives you a lot. You know, each photograph really gives you a map of all of the strains. The rest is just MATLAB and putting in the correct pseudo colors to make it look nice. But the measurements are these the deformations of these little squares.
Sir, one related question. So the strain field that you get, so you use some sort of software or you wrote your own code? I mean, the group has written his own code, because like it's related to digital image correlation, right? Something related to that.
Well, this is not correlate. How do we actually measure them from the, okay. We don't look at a single square, because that's hard. The noise is too great. So what we do is we look at the mean of maybe 3 by 3 squares, and then smooth it, because otherwise we couldn't get reasonable derivatives. But these are technical points. So we're looking, instead of a 50 by 50 micron, we're looking at maybe on average about 100 by 100 micron area, but it's still a local measurement of the strains. But yeah, there's a lot of work that goes into these hand wavings and the graphs and stuff. It's any other questions? Yeah. Move the microphone here. This gives me time to sit down while the microphone is moving back and forth. It's a good thing. Yeah.
Okay, that's related to that question, actually. What I'm thinking is, when you have the grid, and then at that moment, so that's your 0, 0. It's perfect grid at the very beginning of the experiment.
Yeah.
And then the crack comes in and it propagates. So what I'm thinking is, if I want to do it, like calculating the strain, then right here, the grid is not there, where the crack came in. And then this part, it's just completely displaced, this part completely displaced.
Yeah, good question. That's the beauty of these grids, though. What we do is at every instant in time, we keep the label of each one of these little squares. So I'm afraid to go back because the computer will get stuck. But you know, picture okay, these are really distorted squares. I'll make it look like this, actually, as we approach the crack tip. Okay, I remember that this, before the crack arrived, these two, the ij coordinates of these things, I know what they are in the unperturbed frame. So this allows me to, I mean, the point here and the point here are neighbors. In fact, this is the same point in the reference frame, but I can keep track, because for each frame, I keep that labeling intact. That's why this is better than like scratch patterns or something like that, because you have a coordinate system built into the experiment and you use it. Okay, any other questions? Yeah.
Yeah.
Okay.
So does the K2 perturbation go away via the formation of one microcrack? For instance, does it release the stress, shear stress, and then it has to build up again for the formation of the second crack?
A good question. I don't know. I can't, at those scales where these microcracks are 10 to 100 microns, my grid is huge compared, so I can't, there's no way that I can see that. But it's a good question. Actually, I know the answer to that question, kind of. And this will take us to the next part of my talk, which I have 10 minutes, so I'm going to do it faster than I intended, but hold on for 1 minute. There should be a picture here someplace. Okay, here we go. Here's a cartoon. And we're now going to look very briefly at what happens. We've been thinking of the system as two-dimensional. And then your question is perfectly, is a really good question. But in essence, the system has thickness. And the micro branches, there should be a movie here. It's not. Let me try it with this. Okay, yeah. Okay, so these yellow spots are the micro branches. They're localized here. The K2 that I measured is global. So it's not going to get, it may locally get rid of the K2, but globally it's still there. So, and what we're going to do now is look at the effect of these localized microbranches on now, instead of the crack being a tip and singular point in a two-dimensional space where the crack is a line, this crack now in real life is a plane, it's a front that's moving through the material, and it's spatially extended in this way. Now, each one of these microbranches, since it's localized in the Z coordinate, is perturbing that front. So we set up an experiment to see how this front looks like, okay? And the way we did it was, okay, this just reminds you what you've just seen. This is actually a very hard experiment to do, but it's conceptually very easy. We just shined light through a sample, and when there was no crack front, we saw white because the light just passed through. This is transparent material. And at the crack front, the light is diffracted. It's diffracted away from our camera, which is sitting over here. So the crack front we see is just the black line. Any curvature around this crack front acts like a lens to diffract, or to diffract the light away from the sensor. So only the boundary between the light passing through and the crack front, this line will be then the crack front. Technically, it's a bit difficult to do, but it works. So the crack front becomes a moving shadow along the image. Let's see some movies. Okay, so this is a boring crack. So what you'll expect, okay, this is a boring crack or simple crack from the side. This is a simple crack front. Okay, and it's kind of boring. You just see a straight line because that's what the front looks like. Okay, and this is the fracture surface that it formed. Nothing really. This is a bifurcating crack or microbranched crack. I think I can do it at the same time. And this is the crack front. I killed the other. So first of all, you can see that this crack front is, okay, the microbranch increases the fracture energy, creates more surface. The instantaneous velocity of the crack is very sensitive to the amount of dissipation. So the more dissipation, the slower the crack goes. So the crack is going to lag and create this cusp-like region along the front. And we're going to now use that fact to show why microbranches disappear. Okay, so we have now, let me do this really fast because I have like 5 minutes or so. But Okay, let's see. Okay, these lines are crack fronts at different points of time. As they pass here, this is before they meet this microbranch. Okay, this is the crack surface. These are experiments. It's not an artist's conception. And then point 3 is, okay, these guys here, the crack locally slows down and increases its curvature. At point 3, the microbranch dies and the crack front jumps ahead. So we see, this is what we're going to look at. This is what we see now. And so microbranches increase, as we said, the fracture energy. And that's actually evidence for the fact that the energy balance we use to derive the equation of motion is actually a local quantity. The crack over here sees how much is going in, how much it needs, and determines its velocity at that point. And we'll show that that's true in a minute. Okay. Okay. So what we're seeing is a slingshot. So this is, the crack is being stretched, and all of a sudden it can't do it anymore, and boom, it runs ahead. I'm going to run through this very quickly, so don't, if it confuses you, fine. You know, it's not. What I want to show you here is that we can compare the instantaneous velocity of the crack at the moment it gets past it, a microbranch dies. So it's the stretched crack front with what we would compute using the equation of motion that's hiding up here. And the equation of, we see that the velocity is proportional to the energy flux that flows into it, and it's also a local quantity. So here we see the change in the change from the mean velocity in red, and in blue is the change in the energy that's going into the crack front as a result of the curvature. Now these we can independently measure, but I won't go into how we do that because I don't really have time. And now one last thing which is kind of neat. Let me see if it's, okay, this is in slow motion, one of these cusps moving. And we can look at it piece by piece. And what we find is when the crack front becomes a cusp, that's exactly the point where it jumps ahead. Why does it become a cusp? And that's the last thing I want to show you. Basically, it roughly follows something called Berger's equation. Okay. And Berger's equation just says, suppose we have a front that's moving at constant velocity, and we impose a curvature along that front. Just geometrically, this front will create a cusp. It will create a singularity. And okay, so here's Berger, and here's his equation. And all this equation is just taking into account the geometry of the curved front and propagating it forward. And if you have an initial curvature of kappa naught here, this predicts that you'll get a singularity or a cusp within a finite time, and that's what this T star is. So we can measure the curvature of the cusp, and we can measure how long from the time curvature is formed until we get, until the crack derives, it develops a cusp and the microbranch, it disappears. And so we have here two time scales. One is the time scale given by the initial curvature of this front. And the other is just the time scale, which is the lifetime of a microbranch. And what we can show is that very quickly, they're roughly linearly related. So the last thing that I wanted to tell you is that, well, okay, let's go back from the beginning and I'll just summarize what we talked about. First thing we did was we looked at the oscillatory instability and we saw that for an infinitesimal shear perturbation at a critical velocity, this thing oscillates, an oscillation takes place. Good. Then we looked carefully at microbranches and we saw that the threshold for microbranches is also guided by this local, thank you, by this local shear perturbation. But we need a finite perturbation the farther we are from the threshold for the oscillatory instability. So that triggered the onset of the instability, this K2. And now we just gave the answer for why microbranches are micro and they don't just keep going. Because what we find is that these microbranches increase the fracture energy. They locally curve the crack front. And this curvature is actually unstable and creates a singularity. This singularity creates a cusp that has basically infinite curvature at its tip. And the curvature drives, that's actually another infinite energy, if you like. And that pushes the front forward. And that's what kills the front. And that dictates its lifetime. So that's basically what I wanted to tell you today. So I even got to the conclusions. And the take-home message, I guess, that you want, besides the details of cracks and microbranches, this is a small microscopic scale. It all started from this little nonlinear scale at the tip of a crack over there. And that's responsible for all of this stuff. So microscopic scales basically drive macroscopic behavior. And with that, I'll thank you for your attention. Now, we probably don't have time for any questions, but maybe one or two, according to our chairman. My next talk tomorrow, I think in the afternoon, it's something totally different. So if this was difficult for you, that's okay. It goes back to being easy tomorrow. So don't go away is my final advertisement.
Yeah. So time for questions.
So these micro branchings, are they randomly distributed or they show some periodicity?
Say that again?
This micro branching, are they randomly distributed or they show some periodicity?
The onset is randomly distributed, but once they exist, what they do is each one creates the next one, because you have this freedom and this freeing from a cusp. It drives a very high velocity, and then locally it says, wow, I'm beyond the threshold for instability, and it creates another microbranch. That's why you have directed lines. So the initial one is random. We can trigger it by putting in by hand defects, but it's finding some inhomogeneity in the material that's triggering it. But after that, until it runs off of the side of the material, if it does, then it just keeps going. It's self-propagating.
Okay, so I was wondering, you can quantify the spacing between those micro branching and see whether it scales with some function.
It actually scales with the width of the microbranch, the spacing.
Okay.
Again, it's the only scale available in the system, so why not? But yeah, it does.
So one more question.
In the case of cusp formation, is there a minimum crack tip width that has to be there for the formation of cusp? Because if the crack tip is smaller, then the cusp may not form.
Yeah, I mean, if we have I'm not sure. Let me see. It's here in this graph. There's obviously a minimum because we didn't see anything below this maximum time. Okay, so we have there's a maximum time here, which tells us that that's a minimum initial curvature before the collapse took place. But I don't know if we'd done more experiments, whether this would climb up here or something cuts it off. That's a good question.
Okay, I'm sure there are a lot of other questions. We can discuss those over coffee. But before going, we would like to thank Professor Fineberg for this amazing talk.